Combinational logic could be thought of as a cloud of circuits. There is an input and there is an output. The output is going to depend entirely on the input. That is what differentiates the combinational circuit from the sequential circuit that we'll learn about later. Once again, the combinational circuit is a cloud of circuits. It might include things like the AND gate, it might include the NOT gate, or the OR gate. But in any case, the output is 100% dependent on what the input is. There is no memory in a combinational circuit. Our first stop along the way is the AND gate. In English, we would talk about event B and event A. So there would be some significance when both B and A occurred. In ladder logic, you could draw relay contacts. So here's contact B, here's contact A. If both contacts B and A are closed, then coil F would energize. You could describe the AND gate with a Venn diagram. And here we have the possibilities of A, the possibilities of B. The AND occurs at the conjunction when both A and B occurred. So it's this space right here, A and B. The logic gate, that's a very common way of describing the AND circuit. Here's the symbol. You'll notice it has straight sides. Let this be B, let this be A, let this be F. Output F will be a logic 1 when both B and A are 1. It will be 0 if 1 and 0, or 0 and 1, or 0 and 0. What we just described can be put into a truth table. We have input B, input A, output F. The combinations for input B and A are 0, 0, 0, 1, 1, 0, and 1, 1. The output F will be true, which is to say high, when both A and B. So it'll be true here, but it will be false for all other occurrence, because it's only here where both A and B are true. Here's a few more ways of describing the AND circuit. We could use a Boolean equation. Here we would say output F is the product of A and B. You could also write that as A dot B, or A with B in parentheses, or A multiplied by B, or any combination of that. In either case, the AND circuit is a product. Again, the product of A and B. But wait, we're not done yet. We could use a hardware description language. For example, there's Verilog and VHDL. At the end of the class, we'll explore a little bit of Verilog. And in a moment, I'll also show you an example AND gate using a web-based tool. The AND operation could be represented using transistors. Actually, we'll use NMOS here. I'll let that be A. Let this be B. Here's output F. We'll put some voltage up here, so 3.3 volts DC. And down here, we branch off with 2 additional transistors before going to ground. Now, here's a new symbol for you. It's called an inversion bubble. So if we invert A, and here we invert B. The circuit goes something like this. If the circuit is not A, right, so this is 0, we go through the inversion bubble, and this point right here you could think of as 1. If that's a 1, this transistor turns on. So there's a short circuit from here right to ground, which means F is pulled low. The same thing happens if B is 0. So if there's a 0 there, you could think of this being a 1 on the left side of the inversion bubble. At any rate, it pulls the circuit down to ground. So if B is 0 or A is 0, F is going to be 0. However, if both A and B are active, there will be a path through this circuit so that F will be true, which is exactly the situation we described in our truth table. If A and B, then F is equal to 1. The last AND logic representation we'll explore is a map, which is very similar to a truth table. We'll let this be input B on this side and input A on this side. Input A can take on values of 0 and 1. Input B can take on values of 0 and 1. If A is 0, that means this column is 0, and B is 0, that means this row, you will have a 0 on the output of the AND gate. If A is 0 and B is 1, there will be a 0 on the output. If B is 0 and A is 1, there will be a 0. There will only be a 1 when both A and B are active. Let's make a little note here. This is input A. This is input B. And this here represents the output based on the grid of the A and B inputs. To see how the AND gate operates, we can shift over to this tool, which is known as circuit verse. I've already drawn an AND gate. It has 2 inputs, and here is an LED. If A and B are both true, you can see the LED goes on. But that only happens if both inputs are active, which is just what the truth table said. I mentioned Verilog earlier. Verilog is what's known as a hardware description language. So rather than using symbols, you describe logic circuits using language. You code the circuits. For example, this particular code reads like this. It says, I've created a module called AND. It has an interface for A, B, and F. Inputs A and B are defined. Output F is defined. And here's the heart of the actual operation. F is assigned the value of B and A. If you like, we can synthesize that and run it. This particular tool will make a representation like so. And as before, if both A and B, then F. Again, both have to be active in order for that to work. I mentioned ladder logic. This simulation, known as PLC Fiddle, can be used to explore that. Here we have controls. So if we turn B on, you see it went green here, and we turn A on, you can see that F is now on. If either A or B turns off, F will be off. F will only be on if both A and B are active. We now shift our attention to the OR logic. In English, it's B or A. In ladder logic, it looks something like this. Here's a contact for B. Here's a contact for A. And here is our coil F. If B is active, we have a path of continuity that will activate coil F. If A is active, there's an alternate path to turn on F. And of course, you can have both A and B on, and you'll still have F. Just now you have a bit of redundancy because there's two paths that will activate F. The truth table, we have input B, input A, output F, 0, 0, 0, 1, 1, 0, 1, 1, and it will be 0, 1, 1, 1. For the OR operation, it only takes one input to be true. If either A or B is true, F will value is true. Here it's input A, here it's input B, and here it's both inputs. Just like our ladder logic, there's a redundant path. So either A or B will activate F. The symbol for the OR gate looks like this. It's curved, and then the sides curve as well. Input B, input A, output F. The Boolean statement for the OR gate says that F is equal to A plus B, or B plus A. In this case, you can see the OR operation is a summation. That will become very important later on. Again, the OR is a sum, whereas the AND, which is somewhere way up here, was a product. If we go back to our online simulation tools, we can select a gate. We'll select the OR gate. We will delete the AND gate. We'll wire it in and see how it operates. All right, so if either A or B is active, the LED will light. And of course, if they're both active, it will still light as well. Over here in the Verilog world, we can change this. Instead of saying AND, we use that symbol there. Then we synthesize it, and you'll see it will have changed. So now if either A or B is active, the output F will be active. And we can also change PLC fiddle, but we need to add a branch. So we take a branch, we put it here. We'll put B there and A there. Oops. There we go. Turn those off. So if either one, so there's a path through B to activate F. By the way, I should have mentioned in ladder logic, you could think of this as the hot rail. So maybe this is 24 volts. You could think of this as the ground. So what we want to do is we want to provide a path of continuity through to light up this coil. All right, so either path, there are two paths. So B will do it, or A. So again, this path here is from our 24 through A to the coil F. And of course, if we turn on both paths, that's okay. There's just a bit of redundancy there. Our next primitive logic circuit is the NOT operation. In ladder logic, looks like this. So we have a normally closed contact. We'll call that A. And then we have coil F. If relay A is inactive, which is to say the normally closed contact is closed, then F will be active. So you would read this, if not A, then F. Here's the truth table. And that's simply A, F. There are only two possibilities for A. A will be either 0 or 1. So that would just be 1 and 0. So F will take on the opposite value of A. The symbol is like an amplifier with an inversion bubble. The Boolean description, F is equal to not A, or you could describe it as A prime. In fact, there are lots of words you could use to describe this inversion. You could use the word not, bar, as in A bar, which is that guy right there. Let's see, prime, complement, or inverse. In circuit verse, here's the NOT gate. So we will disconnect our OR, and we'll wire it up like so. May as well get rid of this, it's not doing anything. So if this is 1, this will be 0. If this is 0, this will be 1. Right? So the LED will be the opposite of the input. In Verilog, let's see, we get rid of B. We don't need input B. So now it becomes A. If I remember right, it's the tilde. Let's try that. There we go. So right now A is not active and F is, and you can toggle A and F goes out. In ladder logic, we can get rid of B. Actually, we can get rid of all of this. Get rid of the branch. Add a normally closed contact. We'll call it A. So now, let's see, get rid of B. F will take on the opposite value of A. So if A is off, there's continuity that turns on F. If A is on, again, A is a relay in this case, that means the normally closed contact will now be open. You'll see that F is out. At this point, we could go on and we could talk about other types of gates, but I think it would be more constructive if we explored the combination of the gates that we've already gone over. Again, we've only gone over 3. We've talked about and or, and not. We could make a 3 input AND gate. Let that be input C, B, and A. Output F. Output F is the product of C, B, and A. Remember, we said the AND operation is a product. We could make something like a 4-input OR gate with inputs D, C, B, and A. Output F. The Boolean for this would be F is equal to D or C or B or A. Keeping in mind that this here is a sum. So the OR operation is a summation. We could make that 4-input OR gate here in circuit verse. We select the OR gate. Now we need to modify it. So we click on it. You see where it says input size? We're going to increase that to 4. You can see now it has 4 inputs. Here are the inputs. Let's see if it works. If any input is true, the LED will be lit. And it doesn't matter which one. Any will do. If there are combinations where more than one input is true, the LED will remain true. I mentioned that we could combine our circuits. Let's do that now. Let's add an inverter here. So what we've made is a 4-input NOR gate. So it's a not OR gate. And that's the inversion right there. So now the circuit will only be true if all the inputs are off, which is the exact opposite of what we originally had. Moving back to our original circuit, we can convert that into a 4-input NOR by adding an inversion bubble and then inverting the output of the OR gate. We do that by just adding a bar over all of this. So now we've made quad input. We'll call that a NOR. So a not OR gate. Here's another example where we combine gates. Those are both OR gates. inputs D, C, B, A. We'll combine these outputs to another OR gate with an output we'll call F. The Boolean expression would tell us that F is equal to, so here we are at F, we're going to look this way, and we'll see that that is D or C on that particular branch. And if we look this way, we would see that is B or A. So our F is just those two put together. So F is D plus C or B or A. If we remove the parentheses, that's simply F is equal to D plus C plus B plus A, which means we have made a 4-input OR gate. While we're here, let's dig into this Boolean algebra a little bit more. This won't be a complete in-depth exploration, but we're just going to go over some of the highlights so we have a better understanding of how to describe our logic circuits. Now, we start with the order of operations, and this is very similar to math. So PEMDAS, does that sound familiar? Parentheses, exponents, multiplication, division, addition, and subtraction. So that is the order of operation that you perform mathematics. It's very similar for our Boolean expressions. At the very top of the order of operations, you find parentheses. Next is the not operations. So we'll show that is A bar, followed by the AND operation, which we said was a product, a multiplication, if you will. And then we have the OR. Let's just make a note here. So OR is a summation, and the AND is a product. I bring this up now, and I stress it so much because there is a way of looking at digital circuits that we need to know right away, and that is called the sum of products. In order to make any sense of that conversation about sum of products, you must know the precedence rules. All right, I think we've made our point there about the precedence rules. Back to our discussion about Boolean algebra. The next rule is the commutative rule. That tells us that A or B is the same as B or A. It also tells us that the product of A and B is the same as the product of B and A. The distributive rule, A and B or C is equal to the product of B and A or the product of C and A. You could think of that as a FOIL operation. Were we to construct the logic gates, you would have a circuit that looks like this. There's the OR operation with input C and B. So this piece here is C or B. And we're going to AND that with A. We'll let that be output F. This piece is that circuit there. It's an OR gate. You'll recognize this as a multiplication, which is another way of saying an AND operation or a product. That operation is represented by this gate. On the other side, we have an absolutely equivalent circuit that's drawn like this. We have an AND gate with input C and input A. So that takes care of this part right here. We have another AND gate, this time with input B. That's this. The outputs are ORed together. And we'll call that F. These circuits are identical by the distributive rule. We can prove that using a truth table. For the truth table, we'll let this be C, input B, input A. We'll do an intermediate step of C or B, and then we'll show F. 0, 1, 0, 1, 0, 1, 0, 1. Do you remember the pattern we used last time? For input B, we'll let that be 0, 0, 1, 1, 0, 0, 1, 1. And for input C, it will be 4 zeros and then 4 ones. This intermediate column represents that circuit right there. So we're looking for either a C or a B. Right away, we can set all of these to 1 because C is equal to 1 in that case. We can set these equal to 1 as well because B is equal to 1. So that'd be 0, 0. Now we'll look at this part here. We're looking for conditions where A is true and this column is true, because again, that's this input right here. Right away, we can set this to 0 and this to 0, because this input right here must be true in order to get F equal to 1. Continuing on, we look here and here, which would give us a 0 and a 1. F will be equal to 0 in that case. Next, we have a 1 and a 1, which would make F 1. And we just keep on going down the line. So this would be a 0 because of that. This would be a 0 because of that. And 1 and a 1, and a 1 and a 1. So there you are. That is the truth table for this circuit. Now we come over to this side and we'll do another truth table to see if they are indeed the same. Same inputs, C, B, A. This time we're going to do 2 intermediate columns. We'll do C and A, so that's the product of C and A, and another column for the product of B and A. And finally, we'll have output F. So 0, 1, 0, 1, 0, 1, 0, 1. This first column corresponds to this piece here. We're looking for conditions where both C and A are true. We can reject all of these right from the beginning because C is never true for those. And now we look here for C and A. So that's false. C and A, that's true. C and A, 0, and finally 1. This column corresponds to that. So we're looking for conditions where both A and B are true. 0, 0, because B is 0. 0 and 0, because B is 0. Now, looking for A and B together. So 0, that one is true. And here we end up with the same thing. The last step is to take care of the output, which is this circuit here. We're looking for the product of C and A to be true, or the product of B and A to be true. So basically, anywhere there's a 1 in either of these columns, we can make a 1 on F. So 0, 0, 0, 1, 0, 1, 0, 1. So when all is said and done, we compare this with this, and it looks like they are absolutely identical. There's two things you should take away from this example. First, of course, remember what the distributive rule tells you. But the second, and perhaps more important, is the fact that there are multiple ways to make a logic circuit such that the outcome is the same. Again, these two circuits look very different, but the operation they perform is identical. As a sidebar, the next time we come back, we're going to look at some more of the rules for Boolean algebra, and I'll just give you a sneak peek here. If you have this circuit, so that's an OR gate, and this is another OR gate, and you can see that they are run through an AND gate because there's a multiplication right there. The distributive rule would tell you that you can essentially FOIL this, just like you would in algebra. So this becomes CB plus BA plus CA plus AA. This AND gate has some interesting properties. If you were to sketch it, it would look like this. If input A is 0, both of these inputs will be 0, the output will be 0. So in that case, you can see that the output is equal to A. If both inputs are high, again, they are the same input, this will be high. So we can say that A and A goes to A. Now watch this. This term will only be true if C and A are both true. But we already have a term that is true if A is true, which means this is redundant and we don't care what C does. Same here. This will only be true if B and A. But we already have this, so this is redundant. So this whole expression becomes C, B, or A. Anyway, that was just a sidebar. We'll come back to that next class. What we're going to do now is learn how to solve a logic circuit given a specific set of inputs. For instance, suppose this is our logic circuit. With inputs D, C, B, A, and output F. Suppose input D is equal to 1, C is equal to 0, B is equal to 0, and A is equal to 0. Find output F. We start by moving the values up here to the actual inputs. See if we get that right. D is 1, C is 0, B is 0, A is 1. Now, this we can move straight to the input of the AND gate. So that'll be a 0 there, and this one here will be a 1. This signal goes through the inverter, so it will present to this AND gate as a 0, and this 0 will present to the AND gate as a 1. I find it easier with these types of circuits to think about what happens before the inversion bubble, which is to say, I can think easier about AND gates than I can about NAND gates. So if we were to go there, we would see that 0 and 0 is a 0. If we were to go here, a 1 and a 1 would be a 1. After the inversion, that 0 becomes a 1, and this 1 becomes a 0. That brings us to the OR gate, where we have a 1 and a 0, which means f is equal to 1. So given these inputs, f is equal to 1. Were we to use Boolean algebra, the circuit would have been described as f is equal to d bar c. So that takes care of this piece right here. D bar captures this inverter. We can see that C is fed straight into the AND gate, which brings us to this point right here before the inversion bubble. That inversion bubble could be thought of as a bar over this. And now we move on to this part of the circuit, which is an OR. And now for this, it is B not A, which brings us to right here. And now the inversion bubble puts a bar over this. Using these inputs, we could rewrite the circuit as, let's see, so we have D as a 1. So that's 1 bar multiplied by 0, but inverted, plus B, which is 0, so 0 bar, and A is a 1. Let's see if we can solve that a little bit better. So F is equal to, that would be 0 by 0, or 1 by 1. 0 and 0 makes this a 0. When we put the bar over it, it becomes a 1. 1 and 1 together makes 1, but when we put the bar over it, it becomes 0. This is an OR operation, so F is equal to 1. At this point, I think you can see one of the more important objectives of our class, and that is the ability to convert between different representations of logic. In this case, we went from logic gates to Boolean algebra. Here, we went from one form or one representation with gates to another representation of gates. And it wasn't until we went to the truth table, which is yet another way of representing gates, that we're able to see that these two circuits were identical. So with that said, we should go down here and explicitly write what we're talking about. For the rest of our discussion, we're going to take a very shallow look at how to convert from circuit to Boolean to truth table, because all three represent the same information for our logic systems. For example, let's assume a circuit that looks like this. Our opening move is to identify the intermediate wires. This becomes the product of D and C because it's an AND gate. This is the sum of B and A. Now we can look at this gate here, which is an AND gate. So that takes the DC wire and it multiplies it, or ANDs it, with the B plus A. I think you'll agree that was a relatively easy operation. The trick was to go left to right and identify the intermediate wires as you moved along the circuit. Here's an example where we go from Boolean to circuit. F is equal to A or D ANDed with C, or D naught C B naught. As we explore this expression, we can see that this is a 2-input AND gate. This is a 3-input AND gate with 2 inverters. So there's an inverter there and there's an inverter there. All of this together is a 3-input OR gate. So one of the first things you might want to do is draw the circuit this way. So this is output F. Our 3 inputs are A, DC, and D naught, C, B naught. If we expand that out again, we have input A. Next, we have the AND gate. That's our 2-input AND gate for inputs D and C. Then we have the 3-input AND gate with inputs D naught, input C, and input B naught. Those 3 come together on a 3-input OR gate. And finally, there is the output F. Here's the intermediate wires, just for clarity. So that's A. This is DC. And this one here is D naught, C, B naught. Here's another example. F is equal to the product of A naught and B naught, or C. This is a 2-input AND gate, and together this must be an OR gate. Here's input B, input A. We would normally run those through an inverter like so, going to our 2-input AND gate. And we have input C. Together they go to a 2-input OR gate, and there is output F. By the way, before I forget, as a simplification, instead of putting in these inverters like so, you could use inversion bubbles at the input of the gate. So you would read this intermediate wire here as B naught, A naught. And of course, this wire here is C. So F is B naught, A naught, or C. Here's another example. Working the problem left to right, we'll identify the intermediate wires. This wire is B naught or A. And this wire here is C naught, which means the output F is equal to B naught or A multiplied by C naught. Before you leave, I'd like to show you one more thing, and that is the different styles that you can use to represent a circuit. Let's call the first one inversion bubbles. Output F, C, B, B, A, and C, A. With this particular style, you'll find inversion bubbles on the inputs to the gates, and it leads to a relatively compact, relatively easy to follow circuit. Here's the intermediate wires, so that's C naught, B. If we were here, this would be BA. Here it would be BA with a bar over the top because of that inversion bubble. And this wire would be C0A. The resulting output F is equal to C0B, which takes care of that, or the output of the NAND gate, which is B and A, and then a bar over that because it's a NAND gate, or C0A, which takes care of that. Anywho, that's how you sketch a circuit with the inversion bubbles. The next circuit we'll do is one with explicit NOT gates. Let this be input C. Here's the inversion for C, which is shown here and here. So let this be B. We'll sketch in the NAND gate now. That NAND gate had input B and input A. The last AND gate had input A and C0. Now that the input is done, we can focus on the output. If we look at the intermediate wires again, we can see that this is C0, which makes this C0B. This wire is BA, but it's a NAND gate, so there's a bar over everything. And this wire here is C0A, which makes this circuit identical to the previous circuit. Personally, I find this circuit difficult to draw, especially to make everything neat. And it's not so easy to follow because you have to look or you have to follow the wires to find out where they go. Right? It's not immediately obvious that this particular input is C0. There's one last style I'd like to show you, and then we'll call it a day. And this one is the array. Now the array starts with the inputs here. We'll let this be C. We'll put an inverter here, so this line becomes C0. Next we have input B. We'll put an inverter here, so this line becomes B0. Then we have input A and A0. From there, we add our AND gates. We'll let this be C0 and B. I believe the next one was a NAND gate with inputs, let's see, B and A. And the last one was another AND gate with inputs C0 and A. And as before, we'll connect everything up with an OR gate on the end. We identify our intermediate wires. This is C0 and B. This one here is a NAND gate with inputs B, A, and put the bar over the top. And this here is C0 and A. The array style isn't quite as clean or simple as the inversion bubble style. However, when it comes time to actually build the circuit, to sketch it out on paper or to put it into the simulator, I think you'll find the array is relatively simple to use. The beauty comes in the fact that you know where these lines are, right? This is always the C line. This is always the B line. This is always the A line. So while the wires are crossing over each other, you can generally figure out, for example, where this wire is fairly quickly. There's a bit of consistency there. It's easy to follow. Unlike the style in the middle here, which can turn into a giant mess if you're not very careful.